Good morning, Ignite students. Here we go. It's Earth Science. We got some plate tectonics today. So the first thing, if we're talking about deep in the middle of the Earth, first thing I'm going to do is show you outer space from a NASA website. Let's see what we're talking about here. We are still talking about plate tectonics. And we're talking about the movement of these plates. So today's evidence. How do we know any of this? How do we know any of this? Okay. This is Earth's magnetic field. For the most part, the magnetic field around Earth is just about the same as if you had a giant bar magnet in the middle of Earth. It's pretty close. So it's a good analogy. So we've got North Magnetic Pole, geographic North Pole, 11 degrees. Geographic South Pole, South Magnetic Pole. That's a reminder that the Earth rotates on one axis and the magnetic field is tipped over slightly. Okay? They are not the same. So there's only a few degrees between them. They're pretty much the same. If you took an old-fashioned compass and followed it straight north, you would not end up at the North Pole or the geographic North Pole. All right. Thing two. I thought red was north. Why is red pointing down here? Because if the Earth has a north and a south, what on my compass I call north, what I'm calling north, the only way it's going to point that way is if that inside the Earth is south. Otherwise it flips. So if the north end of this needle points to the up here, that means inside the Earth that has to be a south. We still call this normal field, normal polarity. At times in Earth's past, that's been reversed. It is flipped around 180 degrees the opposite way. And we'll talk about the consequences of that. In fact, paleomagnetism. There's a word. I know all the things in it, but I have no idea what that is. Like, paleomagnetism is the history of Earth's magnetic field. Let's just call it that. Magma has iron in it. It has magnetite in it. You can go out and find random rocks that have some magnetic properties. You can go out and find iron that has some small amount of magnetism in it. It can be made into a permanent magnet. Here's what happens. As magma, whether at the bottom of the sea or in a volcano, comes up through the Earth, it's molten. It's completely liquid. And so all the iron in the magnetite, in it is randomly oriented. As it cools down, all those little bitty internal compasses that give it the magnetic properties, they're molten. They can slowly align to north-south on the Earth before this hardens and crystallizes. It's slow. It's not perfect. But it happens. So what in the world is this paleomagnetism? How do we even know this is a thing? This is a picture of the mid-ocean ridge. All right, let's blow this up here. Ooh, we saw that coming. All right. As molten lava comes up, it settles down here. As those two move out, you get this area where everything in there, all the iron is facing one direction, it's facing north. And then you get this other area where it's facing south. And then north, south, north, south, north, south, as this area grows. This is a slow process. Okay? It takes tens of thousands of years to do stripes at a time, and you'll see they intentionally draw this jagged and uneven because how in the world do they find this? They take a big boat and they drag a magnetometer across the seafloor. When it's over one of these orange strips, so this is now, when it's over one of these orange strips, there is more magnetism than you would expect. Why? Because you've got Earth's magnetic field that you're measuring, and all the magnets in these rocks are lined up together, so they're increasing what's going on. Now, in these white sections in between, there's almost no magnetic field because Earth's magnetic field points one way. The magnetic field from these rocks points the other way, and it really diminishes and lowers the total amount of magnetic field that the machine is registering. So you have high intensity magnetism for these yellows and oranges, and you have very low intensity magnetism in these white areas. And you can measure that. And the fact that it's symmetric, it's book-ended, it mirrors all of those things, and it's smooth, it's even, that's some of the strongest evidence there is for seafloor spreading. Let's get back. Okay, that is definitely something's going on here. We gotta reset the image size, but the whole rest of the page is all sorts of funky. We gotta fix that later. Whoops. Same thing. Here's an image so you could see this is brand new crust. And then this is a little older, a little older, a little older, a little older. It's symmetric. Guess what? They've also know the dates of these. So in addition to the magnetic field, the dates are new, a little older, a little older, a little older, symmetric, moving outwards. It's really strong evidence. How do we know the dates? Glomar Challenger. Okay. Late 60s, 68, maybe it was commissioned. This boat went from 68 to 83 as part of the deep sea drilling project. And it goes around the Pacific, the Indian, the Atlantic Ocean, and it drills down several hundred meters into the sediment, into the top of the crust. And it pulls up these cores and it dates these cores, and you plot where that is on the Earth and the age. And what you find is the further away from the ridge you are, the older the sediment, the older the drill sample. The closer to the ridge you are, the younger the drill sample. And so they did this all around the world, or in several different oceans. The dates and the ages matched up. They found nothing older than 180 million years. So the last two meetings, I showed you that video of that whole Pangea turning in, because the entire ocean floor, all of that, has moved and shifted in 220 million years, give or take. So there is no ocean rock older than that. It's already subducted back under, it's back in the earth, remelted and reformed somewhere else. If we measure continental rock, we can get almost 4 billion years. That's 2,000 times older. Okay, well, yeah, 180 million years or 220 million years, right? So if it's 200 million going to 4 billion. No, what did I say? 2,000 times? No. 20 times. 20 times. 20 times older. It's 200 million, 200 million, 200 million, 200 million, 200 million. Do that 4 times. Yeah, that's it. Gets you one bit. Yeah. Here's the Glomar Challenger. It is a boat. Some of these pictures are nice and old. A couple things about the boat. You guys are going to have a project this week where you're going to look something up and you're going to report back to me what you found. So the Glomar Challenger, that's the age. Now, we've got paleo paleomagnetism. We've got, so using the magnetometers, we have earthquake evidence. We're going to talk about earthquake evidence, but we're going to do it when we talk about earthquakes. So earthquake evidence is strong. Glomar Challenger did the dates. Last thing, hotspots. Hotspots are good evidence of seafloor spreading. This is an eruption on the Big Island, okay? The Big Island of Hawaii, all right? That's just a good site, the National Geo site there. Here's what's going on. This is awesome. There's a hot spot down into the mantle over here. And there's this plume of hot, super hot gas that's rising up, rising up, rising up. But this plate is moving over it. The oldest of the big islands out here, Kauai, no volcanoes. Oahu, no volcanoes. No volcanoes. Maui, one pretty dormant volcano. Or one that might reactivate. Probably not, right? Hawaii, Mauna Loa is dormant, Kilauea. There are active volcanoes on Hawaii we're going to look at in just a minute. And this right here, it's already named. That's going to be the next Hawaiian island. There's already a spot when this magma has found a crack and it's working its way up and it's building a mountain under the ocean. And it's going to continue building and building and building. The whole thing is, this whole plate is sliding like this. The hot spot in the mantle of Earth isn't moving. Here's the Hawaiian Ridge, and this is a chain, older, all the way here. This is Alaska. This is the Aleutian Islands and the Aleutian Trench right there. So this whole Pacific plate is moving right now northwest. How do I know northwest? Look at the Hawaiian Ridge. It's right there. That's the direction this is moving. All right, this is the Emperor Seamount. What is a seamount? Okay, it's not something from Aquaman. A seamount is a mountain that doesn't break the ocean's surface, but it is a mountain because of where it begins. You measure the height of the mountain we measure the height of Mount Everest from sea level, where it starts, because it's built on top of the crust. You measure these from the sea floor, where they're built up from. Hawaii, the big island, Mauna Loa, is the tallest mountain in the world if you let it count where it really starts from down here at the bottom of the ocean. But that's not the way it's measured, so Mount Everest it is. Old, really old, medium, young, brand new. So there's a hot spot right there, and this whole plate is moving that way. All right. This is earth science. You need to see more of this, and it's not easy to do online. I don't want to play a video while I'm talking and have you just watch a video that you could watch on your own, but you need to see some more of this. This is actively happening right now. It started December 20th, okay? So what is that? Through the 31st, that's 11, and we're at 23 days. This is an ongoing eruption of Kilauea. All right? The 2021 Summit Eruption Photo Gallery. All right, well, hold on a second. Hold on, let me take this out. All right, this picture was taken December 24th. Here is Kilauea. It had hardened. It had cooled over. It was solid, which means as it rains, you get a lake. You get a water lake in this summit dome of Kilauea. That's December 20th. Let's take a new picture, December 24th. That's December 24th, the exact same shot. Same location, same steady cam. This, obviously, so right here, we get an eruption, and it fills. So you also can notice the height. Look at the background. The background is not changing. So you can notice the elevation change. The lava, see, since it's broken the surface, it's lava. In the earth magma, above the surface, lava. So is filling this thing incredibly rapidly. It's rising up. Okay? All right. This is worth a minute. This is the dome fountain. So January 2nd and 3rd. Some of these videos are taken. This thing is 16 feet tall. That's the scale. We got to get our scale right because this, so you can see, relates back to this image. It's that right there. So now you could see how huge this is as it's spewing all of this up onto the surface, because when you get in, if you put your finger over the end of a water hose, the water comes out faster and goes up and out. When the opening this comes through narrows down, that magma picks up some speed and it comes up and out. So that's what the dome fountain is. These can occur when lava rapidly emerges from a constricted vent or fissure onto the surface, or in this case, beneath the surface of a lava lake. That is a lava lake. This is crazy happening right now stuff on Kilauea. The earth is alive. Like, it's erupting right now. It's windy on the top of a mountain. Okay. That's huge. Some of the first scenes, it's not a great video. It does show you that all that water that was in there, it shows you some steam, just plumes of steam, because you got lava that finally erupted and broke through and is boiling all that water. And you got lots of, here, approximately December 20th, 10:30. That is gas, that's dust and debris, that is ash. But there's also a whole lot of steam in here as you boil away that lake. Activities, this is the lava's cascading, falling down back into the base, December 20th. Oh, there we go. So this is from the other side. Aerial photo the next day. 2 of the 3 original vents feeding the lava lake. And it says would soon be submerged. In other words, as this lake fills up, it's going above the location of this. So you don't see it anymore, but it's still feeding it. Just some really cool, crazy pictures. Crater Rim Trail, approaching the overlook. When it's not active, it is a national park. Put that on your bucket list. That's crazy. It's January 2nd, right? It's absolutely crazy. Oh, look, you got your rainbow. And some of these, you will see this view is not available from publicly accessible areas, meaning that scientists went in and it's off the trail. You cannot see it. This is the name of the crater. This will take 1 more minute real quick. Glance at this. So in 2018, the summit collapses, and so what was stable drops down. Now you've got the water lake, and now you've got this. So before, after, when we say the summit collapsed, literally a hole falls in. And you can see the trail zigzag right here, as close as people were allowed to get. It seems a little more dangerous right now, okay? 2019, you get the water lake. So before, and then water. So it solidifies enough to start holding rain. And now, 2020, the one we just saw, awesome. All right. And again, where? That's Kilauea. It's one of the newest, youngest, most active volcanoes in the Hawaiian chain. All right, I will get you an assignment, guys. Have a great day.